So I'm going to be discussing a little bit more of everything, but before to start, I want to mention that a little by little, some more students are sending me the pre-test results, and that's great. I actually posted on the Brightspace your results for the pre-test. They're pretty good, but make sure that you send it to me over weekend so you get all good start, and that will cause you starting with a perfect grade for the class. And I guess it's always a good idea to earn the perfect grade. And that's our goal, to be done with this class with an A grade, right? And I will do my best to help you out, which means I'll be bugging my students and giving them another chance to fix things up. So you also need to do something on your side. That's the message. So anyways, please think about it, and let's start with more of review. By the way, if you send me the pretest and you don't see a result on the Brightspace, please let me know that, because maybe I missed it. Maybe it's my fault. Just make sure that you actually send it to me, because sometimes you're trying to send something and it just sticks in the send mailbox or in drafts, right? In drafts, and it never gets sent it, whatever reason. So just make sure you double check it. All right. So, anyways, we are here to do calculus, and it's based on, you can see lots of formulas are from trigonometry. You can see that there's everything with arcsine, arctangents, and everything, all this beautiful derivative types. There is also hyperbolic sine. That one I'm not going to worry about. It's very rare. Maybe you'll find about a section in the textbook and we will never see it again. So I'm not planning to look at that much, as long as you are fine with it. So the hyperbolic, they just to fill the space. So we'll be concerned pretty much up to formula number 24. And the concern is to make sure that you realize how it all works and why this is here. Otherwise, some people have a bad start. They're just looking at the everything and don't feel already comfortable. So I want you to start to get comfortable, to refresh your memory or to learn what's going on. And the reason I look at this differentiation formulas from Calc 1 is because from the Calculus 2, we actually use them to find antiderivatives. And you're already familiar with antiderivatives. Should be from Calculus 1 class. So if you know how to take the derivative, let's say, of function, what we did last time, sine, right? That's cosine. So you're going kind of backwards. And if you take derivative of cosine, that's negative sine, or of negative cosine, it'd be positive sine. So these things are going backwards. And since they're going backwards, this is really like a half of the page that we are going to be concerned with. And my goal is to refresh your memories and to show how they all are coming up. And let me try some of those. Let me say, try to start with, I think last time we did something with sine is cosine or negative cosine, whatever. So now we're gonna try, how about tangent? That's another very popular kind of formula. So let me start with derivative for the function tangent, like exercise, actually formula number 15, and see how we differentiate tangent. Tangent, which is sine divided by cosine. So it turns out that we're gonna need to find the derivative of a quotient, right? There is a special formula for the derivative of quotient that is a little bit unpleasant. So usually we're trying to get rid of the quotients, but sometimes we can't. In fact, in most cases we can't. So what the formula says is square of denominator. Remember the formula? Maybe I can write it out. So what if you divide function f by function g? That's very popular kind of structure that appears in lots of exercises. So then taking the derivative of it will square your denominator and then go f prime g minus g prime f. You can write it any way you like, as long as you understand that they commute with its product. So again, to prove this, we utilized, it's quite a lengthy procedure, but we utilize the formula for derivative. If you want me to, I can definitely take a look at it. It is also in the text. But anyways, just think about it. It's always a good idea to feel comfortable. So I need to take derivative of numerator, which is sine, which is cosine of x, and then you multiply it by your denominator, which is another cosine. And then you need to take derivative of your denominator, g prime. So that be derivative of cosine, which is negative sine. But since I subtract, I have to add because it'd be negative sine and subtract it, so that'd be positive. And again, I multiply in sine of x, the derivative of it, by another factor, which is my numerator, which is another sine. So we get to utilize the most popular formula in trigonometry now for our numerator. And that most popular formula is the fact that square of sine and the square of cosine added together give us 1, right? So that's, I guess, number one trig identity that you utilize in a lot, really a lot. So if I add them together, the formula stands for 1, and that's a derivative of our sine or tangent. And why did they write it like that? Well, first of all, 1 over cosine is a 1 over, it's a secant, right? So since it's 1 over cosine squared, it's a secant squared. And then they use so-called composite functions. So it could be some not just nice variable x, but function u of x. So you have a chain rule that says multiplied by also u prime. So it's not if you take derivative just of tangent, but if it's derivative of 3x or whatever under the function tangent. So it's generalizing more serious case, and you can see that u prime is present everywhere. It's kind of formality because technically that's what we're using. So anyways, when we return back, so if you are trying to go backwards and if you try to go from the result of your derivative back, so if you take antiderivative of secant squared or 1 over cosine squared x, and we also must put dx next to it, we're gonna have to get a tangent. And that will be the formula that appears here in the, where is the secant squared? Secant squared is a little bit lower. So I need to scroll a little bit down. That's scroll a little bit down, and you can see secant squared is exactly tangent. But they use letter u or x. It doesn't really matter what your variable letter is, right? So that's something that is good to notice. So my goal for today is to keep selecting a few formulas that I think are good to select, and little by little get a little more of it. And of course, I don't plan to show every single formula, because if you know how to do formula for tangent, then you can also do the one for secant squared, then you can also do the one for cosecant squared, which is going to be tangent, right? So that secant with a tangent and cosecant with a cotangent, but the sign comes out as negative. It's a good idea to try to see why this is negative comes out, so just for purpose of feeling better and more comfortable. Well, the most challenging ones for making sense are ones for arc functions. So if I take a look at, for example, arc sine, so y-its derivative has 1 minus x squared and denominator inside the square root. That could be a great thing to wonder about, right? So, and the similar formula to the one number 19 I'm looking at right now will be 16 here on the bottom. So it's going backwards to arc sine, right? You take antiderivative. So how can we check out the validity of those formulas? And that actually brings us to the test questions. So let me recall what we did on the test, because I really wanted to do the problem for you from that pre-test. And let me see where this is could be found here. Find this out. This is my pre-test. So, 208. I just want to check out the pre-test because it was interesting calculus. Okay, that's from the student. I'm trying to find the pre-test. So see, it's a little bit challenging to locate something when you are in Outlook. You probably already know. Oh, here it is. Pre-test. When we have a Gmail, used to have a Gmail, it was much faster, but with this Outlook is, well, it gives us challenge, so it's great, people say. So I'm trying to do an exercise number 4 for you now from the pretest, which you already familiar with some of you, but I think it'd be a good idea to try again to make sure that you all see and feel comfortable with those steps. So cotangent, because that's same ideas that I will use for the working out my arc function derivatives. Like in this case, it's arc cosine or cosine inverse. Sometimes people write arc cosine, which is the same thing. Now, what should I use instead of E? Well, whatever, 1, 2, 3, 4, I can say 1. So it'd be 1 plus 1 is 2 over that square root. See, Alex, why did you put square root? Well, usually it comes out. We will see why. Technically, it could be some number other than that. It should be just large enough, bigger than whatever we have, 9 squared, the largest one. So anyways, this is our exercise. And I had to find the exact value of this expression. It's in terms of numbers. And since it's exact value, it should have a square root in it, right? So I call this as a cotangent. So that's a standard way to solve it. Of course, you already know that number of ways are possible, but standard way is to call this arc function as a y. So my function y will be arc cosine, right, of whatever we have here, 2 over square root. Okay. So now, of course, I want to get rid of that unknown, annoying arc function. And we utilize its inverse cosine. So please notice this is function of x. So y is kind of x. So I could, so technically you could put this in a calculator and get the number, but they want an exact value. That's why this whole thing starts. So cosine of y is gonna be found as a fraction 2 over square root. Okay, so now what is the cosine? You remember, if you have a right triangle, and for convenience, I will take hypotenuse 1, because if it's any triangle, you can always divide by hypotenuse all sides, so you get 1. It'd be similar because angle here is y, and its opposite side and the adjacent side. You ever see that before? Adjacent, and that will be a hypotenuse. And the reason I write it in this format is because of definition of function cosine that comes now from the right triangle. It says the quotient of adjacent side over the hypotenuse. So that's another way to define function cosine. Please notice that's angle y. And please notice there was no y in the original exercise, so I came up with this y for convenience to show how this whole process is usually being done. And that's, again, for the future, for the next formula proof, because it'd be exactly using the same steps. So adjacent and hypotenuse. So it looks like we have adjacent and hypotenuse. And here, so I can declare that my adjacent side is going to be I shouldn't have put 1, I just put square root 205. 205. That's a quotient, so it doesn't really matter what it is, and because quotient will hold the same, and the adjacent side is 2. And that way I can find what the opposite side is, because this is a right triangle. So that's the key side. So if we know 2 sides using Pythagorean theorem, I can always find the third side. So I can say that the square of opposite, maybe I can call it using some letter for convenience, x plus, so squares of adjacent on the opposite sides will give me the square root of that hypotenuse squared. And you probably now start to see why I put square root. So it disappears when you square it. That's why it's standard, they say. So, and that way you can see what your x is. And why you need to see what your x is, because your equation is in finding this so-called cotangent. And the cotangent of y will be a quotient of cosine over sine. And when I need to get that sine, I need to have that opposite side, right? And the opposite side is what we're just working on. So the opposite side, x squared, will be actually 205 subtract 4, or 201, and then we have x is equal to square root of 201. And that's what will give me ability to write what the cosine is. So if I want to go for the cosine, well, cosine is already here. Cosine is here, so sine, it's friend sine, because I need both sine and cosine because I need cotangent, right? That's cosine over sine, so sine of y is a quotient of the opposite side by the hypotenuse, right? And the point of story, we found that opposite side, which is x, which is square root 201, and we divide this by our hypotenuse, which is the square root of 205. And now we're done at this stage because we have everything in here. So I think I will clean a little bit of room to write it down. So once again, this is a standard procedure in solving this trig stuff using arc functions. So it doesn't really matter. You have arc cosine, arc sine, arc tangent, arc cosecant, or arc secant. It's all the same thing. And it's one of the ways. Of course, there are other nice ways, but we don't want to start wasting time on doing the other. So when I divide cosine, which is what we already know, this fraction, which is here, 2 over square root 205, and I divide this by sine, which is one we just found here, square root 201 over, again, square root 205, then my square root 205 cancel, right? Because I can multiply and the top and the bottom by it, so they will go away, and I ended up with the answer, which is 2 over square root 201. So that's for the case your a was 1, if a was 2, then you would get 3 over square root of 2, whatever, 200 probably. So you can check this out, or maybe something else. But anyways, it's a good idea to get a pen and to write it down. I would highly recommend you to do it if you did it some other way, because that's, again, exact value because it consists of square root present. And this process of thinking is going to be, I believe, encountered again in the future. And now I go back to the textbook because my goal is to use exact same approach to take the derivative of arc sine. So now I need to take the derivative of arc sine. So let me do that. So arc sine, which is sine. So how can I possibly start this? Well, I need to recall the definition. So it's actually sine of x, and I call it as y. So just the same exact plan. I don't want to have arc. So I'm going to apply function sine to both sides. I say, Alex, is it always going to be the same thing to get rid of arc? You always apply. Technically, yes, but I have to be careful with the main and the range. I don't want to overload you with that. But turns out if you're in the first quadrant, then it works because otherwise it needs to be in the correct part of the main. So that way you end up with sine and arc sine that cancel each other out, and you end up with only x on one side and sine of y is on the other side. So the point is, you know how to differentiate function sine, which is here right now, but it'd be implicit differentiation because it is really not just the sine of letter y, but sine of function y of x, right? Because function y is arcsine, so it's arcsine of x, so it's function y of x. So if you take derivatives on both sides, then derivative of x will be 1, but derivative of sine is a cosine. Last time we already noticed that. And it's not obvious, right? Remember, we went through quite a bit of pain, but since it's a composite function, it's times y prime. And from here, I can actually see what my y prime is going to come out. Since I call it as y, then y prime is going to be 1 over cosine of y. I say, and that's it, Alex? No, because the problem is there is no y in the original question. See, that's why we have to go through the same process, because this is really function y of x in the original question with arcsine did not have any y. We use y for convenience. So now we need to boil it down to x itself. So that's the whole point of the procedure that I was doing here with right triangles. So I'll have to repeat this again. That's the way it is. So what should I repeat now? Well, looks like now I need to look at my right triangle. And once again, I think here we'll use 1 because it is. Write it down because I was away. So x is equal to sine of y. So that's where we started, right? And it's it is a trick of trigonometry. So it's x, so we have to divide it by 1, so it'll be our hypotenuse expression because we need the opposite over adjacent, right? Or opposite over hypotenuse. So if we call this as y, definition of the opposite side divided by the hypotenuse, that's our sine. So again, sine is opposite over hypotenuse. So that's where it all starts. Starts what? Starts proving the derivative of arcsine is whatever they have here, some questionable expression with a square root. And why is it going to be with a square root? Probably now to start to get better feeling because of Pythagorean theorem, because now I need to find the adjacent side, and to find the adjacent side, I need to use Pythagorean theorem. So it'd be square root extracted from hypotenuse squared, subtract the opposite side squared. You can write down exact same expression for the triangles. Let's say you can call it as whatever letter z, so z squared and x squared is 1 squared, and then you can pull out z. I don't want to bring another variable in here because we don't need it. So we just need 1 minus x squared. Because now we need to write down what our derivative is, and I need to take cosine of y, so I probably can write down the cosine first. Write it here. There's not much room, so I'll write it here. Cosine of y, which is what? Well, that's adjacent over hypotenuse. So that's a square root. Right. Adjacent hypotenuse. Sine is opposite over hypotenuse. So this is, again, all comes from trigonometry, heavy use of trigonometry. That's why we are doing it for a refresher. So adjacent side is that square root of 1 minus x squared, and the hypotenuse is over 1. And since I need to take its reciprocal, then I go with the denominator, which is flipping 1 minus x squared. Now it's in the bottom, now it is in denominator, and that's 1. And notice this is what we have for derivative. And we already know that the u prime, that's because of chain. So we just justified the formula, right? So now I know it's now getting a little bit too overwhelming, but technically I did the same procedure with the right triangle and for the pretest as well as for justifying the formula. So I hope you can work out one of those for your homework. And some students say, Alex, I'd like to do it after this lecture right away while I'm still fresh, because tomorrow I'll forget everything. So that's why I think it's a good idea. And the second part of class, I'll let you work it out, right? So you take a little break, and then at your own convenience, you can do that. Or else, if you're tired, do it over weekend. So whenever it works for you, because I know for different people it works differently, and I'm absolutely fine. So anyways, so looks like now we want to, since we know derivative, to look at the antiderivative, because for the antiderivative, there's an arc sine. Where's the arc sine? Here, 16. We also have some constant a that appears, and that's what I wanted to do for the end of this. So to look at the antiderivative stuff. And the antiderivative now needs a little bit of simplifying. So I need to also add one important fact here now, that derivatives are good and antiderivatives are not. Say, Alex, are you serious? They're friends. Well, you can find derivative of any function. But for antiderivative, there is a problem. Antiderivative, there are just few of them that you can find. And of course, we will talk more and more about it. You probably heard it when you took Calc 1 class. That's why they have those tables for antiderivatives, because for derivatives, they don't have any tables. So anything that you have in these formulas, all functions that you work with, they have derivatives, and then the rule of derivative of composite function takes care of this in any way you like. But if you start to get composite functions when you deal with antiderivatives, it's not that simple. In fact, new theories appear, and lots of times you just can't do it. And that's the issue. And that's why differential equations class appears, because it's really not differential, but antiderivatives that you're trying to calculate, because there's various antiderivatives that people take, and they put them in the groups and they put them in a table. And if you say type in Google the table of antiderivatives or various integrals, I think they already have more than 3 million of them. And they're all composite of the functions that we know how to differentiate. So the problem is antiderivatives, turns out, because it's not that simple. So we do some of those, and eventually we say, okay, the rest we just give up on, because you can work on it all your life, because you say, as I said, 33 million formulas plus, and there'll be more, of course, by next 20 years, we're probably going to be 4 million that they produce. So Now you say, what is this for? Well, that's why they find some other approximate methods rather than to take it directly and precisely. And that's the idea. So anyways, that's interesting story, but that takes us a little bit away of our point. So how can I find the antiderivative here? So technically what we just saw is that if I try to integrate exactly the derivative, and where is my formula? Here, it's here, right? Alex, so where's your answer? Well, here's the answer. So derivative of my arcsine is right there. I can write it out so it's better visible. 1 minus x. So the point of story, it has to be 1. It's not 2, it's not whatever number is a. So what if you are trying to integrate? So let me write it. So if I put it as 1 minus x squared, then everything is nice because we have arcsine of x plus the constant. It's always plus the constant, right? So that's standard. So it's not just one function, it's a family of functions. And that's another little extra I have to add to this story. Because of this plus constant, it means you can add 2 and it will be antiderivative. You can add 3, you can add pi, you can add any number. So there are infinitely many answers. It's a family of functions because when you differentiate the constant, it becomes 0. So it gives you that expression you integrate. So it is really not one, but the entire family. It's infinitely many functions. And that's another important thing to realize. That's why it's always plus the constant when you take antiderivative. And there are some problems with that actually asked to find particular constants, and that's where we start with the differential equation story. So anyways, what if it's not 1? What if it's 2? Or what if it's in general a? People say it's a squared here. Does it have to be a squared? Well, you can write 2 as a squared because it'd be nothing else but square root 2 squared, right? So your a will then be just square root of 2. So as long as it's any positive number, in other words, you're fine. So how do we find the antiderivative in that case? So if we put whatever number squared in here, and again, it could be number such as a square root, so doesn't matter. Just for convenience, they decided to use squared. I'll put minus x squared, so I don't want to mess with you right now, it'd be too much. So a squared. And how do I get 1? Well, it turns out I need to pull it out. So I need to take out a on the top as well as on the bottom. So if I factor out a, what's going to happen? Well, it looks like if I try to, for example, divide by 1 over a in here, and denominator. So in order not to change my fraction, I need to do same thing with its numerator. So it could be canceled. And that's the reason why you can see that a appears in your denominator. So let's do this a little by little. I just want to maybe to just keep 1 over a here, and then dx, and then I want to bring this 1 over a inside my square root. How? Well, I need to square it and square root. I'm trying to say it's a square root, and then I square it. And that way I can distribute it over here. And that's the reason why I'm trying to get that number 1, right? Because my goal is here. My goal is to have 1, not a squared. So now it looks like when I bring it in, it'd be a squared over a squared. So I produced my 1, and minus, I now have x over a that I can also say it's squared. And now we can use our formula. Let me first of all write it down. So it's still 1 over a on the top, dx. And then on the bottom would be that number 1 I needed really badly, 1 over a, and that's x over a squared. And now it needs to be done by substitution, right? In order to take the antiderivative, remember, since we can take the antiderivative of x squared, so I need to rewrite it as some new variable, let's say y. I say, Alex, we usually use letter u. Okay, use u. So then I take derivative of both sides. So I take derivative of the left side, that'd be x is differentiated, a is a constant, so it'd be just 1 over a was dx, right? And that's du. By the way, sometimes people wondering how come you attaching this dx over du to both sides. I think it's a good idea to write it down once a little bit slower. So I need to get some. See, there's lots of things that you probably did in the calculus 1, which is integration using the substitution. And I'm going over little by little the stuff you learned in the previous class. And again, the reason is we're going to use it again. That's why it's called calculus part 2. And I know that sometimes people can take calculus 2 without taking calculus 1. And I had a number of students of that type. So that's why I decided, why don't I just do everything from the scratch? So people learn Calc 1 while they're doing Calc 2. Why not? Or if you forgot it, some people say, I took it more than 10 years ago. Okay, that's fine. You don't need to go back to Calc 1. We're going to see it all anyways. Just ask me questions. If something is not clear, just ask me, Alex, why? And we'll go to more details because it's fun. So anyways, what did I try to tell you? I tried to find derivative of x over a on one side and function u, which is a variable we have is x on the other side. And this one is a constant. So when you take derivative, when something is multiplied by the constant function, that constant is just being factored out. So a in denominator, like 1 over a gets out. X is in numerator, so derivative of x is 1, right? You know that derivative of x was 1, which is good to realize. And then u function of x is du over dx. That's another way to write derivative. I don't like this way because it's a little bit tedious, but for this particular case, I think it's good because now you can multiply both sides by dx and see why this variables being separated, because du stays on the left side, just like we have here, and dx goes to the du stays on the right side. This is right. Dx goes on the left side, so 1 over 8 dx. So once we have that substitution performed, notice that our integral, so now I need to go here. So our integral will have a numerator, which is just a du. So this whole thing will replace with du to help us integrating. And that fraction, x over a, will be u. So we ended up with exactly what my formula wants, right? And that's going to be my antiderivative. So the antiderivative, which is arcsine of whatever variable we use, arcsine of u plus the constant, but now instead of variable letter u, we put back our substitution, and our substitution was x over a. And that's the reason why this over a factor appears in the formula. And the formula here is u over a. So because otherwise, how come it's over a? In fact, if you look at the others, it's always u over a, but with case of arctangent, it's also 1 over a appears, and it's all here when you do the substitution, turns out. Of course, if I start to prove you entire table, it'd be taken forever. It'll be just going over Calc 1 once again. But if you want me to, I can always do another exercise like that if you prefer. In fact, I thinking about doing another formula. I think the good one is 15, which is analog of 14, but I think it'd be too much for today with this, right? So I will maybe do it on Monday if I don't forget to remind me. So I think that'd be another formula that's worth to verify. So secant, and that's the one with secant tangent. It has a substitution, so it'd be, well, anyways, let me leave it for Monday, Tuesday next week. So what else? I want to end for today with one very important fact, which is called fundamental theorem of calculus. It's fundamental. It's big. So let me stop. Let me clean all that. It's all recorded, so you can always look at it again after the little break if you want today. So fundamental theorem of calculus, I think it's a big deal, and I want to really look at its proof. I'm sure you know fundamental theorem of calculus, right? But why is this working? Because sometimes it is very questionable why. And it's working because of mean value theorem, turns out. Mean value theorem for derivatives is what we're using. So where's our fundamental theorem of calculus? 4.4. See, it's all again in the stuff related to our calculus 1, first 5 chapters. So to get to 4.4 is page 282. So I want to go at about 35. So I'll be like 200 and no, 15, I think. So it'll be about 300 or something. I hope by now you already have downloaded this textbook for just in case, because we used to have another free textbook available on Google. It was calculus textbook of the same authors, same edition, but it was dealing with Calc 1, 2, and 3. And now they took it off and they put for free Calculus 1 and 2. So Calc 3 is gone, but it might appear. So that's quite amazing. One can say if I take antiderivative, so the key part is that f prime is the function f of x. So if I rewrite my statement of fundamental theorem of calculus with the antiderivative only, it will start make a little bit more sense. So f prime of x, this antiderivative function that we know when it's differentiated, we get our function f back. So, and now here's the amazing thing. So now we go from upper to lower. So now it's definite integral compared to general indefinite. So we have upper limit minus lower limit. So it becomes a number or the area under the curve right? The integral. So if you have some kind of curve, f of x, or you could call it as antiderivative, and then the area of the region below, you can just take the antiderivative function, f, capital F. It's not the same. It's not f, but it is capital. It's a big one. Right? F of x, and from A to B, the area of this region is, don't want to mess it, just is going to be integral the same as area. And we can find the integral and we can plug upper and lower values and get it. So how do they justify this? I just want to give you an idea of justification. So they break this into close to infinitely many pieces, because then they take the limit. And then in every piece, they say they can use mean value theorem. So for every piece, you basically treat it as if it was a rectangle. So they say if you have a rectangle and there is a upper part is going to be designed from that function capital F, there is existence part that being used. So there is some point C, there is some point C, and that's actually the weakest part in the proof, because existence, we say it exists, but how do you find that point C? Well, that nobody knows. So it exists. And they say that's the point C that exists such that we can use it. So, but how do we find it so we can use it? Nobody knows it. That's a weak spot in the proof of mean value theorem. If you start to think hard on it, and that's what people sometimes do when they take advanced calculus classes, so they start to have a hard time finding this point C, because for some application it is important. So anyways, so that function f prime derivative, but now it's at point C. See, sometimes people don't know it. It's x changes with some other value, becomes that. And that other value is fine because we don't even use it any further. We just use the upper value at that point, whatever analog of A, there is x I or 1, whatever you like, I, and then the next one is going to be I plus 1. And then the gap is difference of this, which is also called as delta x on the bottom for convenience. Delta x is fine. So that's how they turn this into and divide by delta x, and that's actually the formula for derivative. Remember, we last time saw if you have this f of x minus f of x plus delta x over delta x, that was definition of derivative. So that's mean value theorem. So the point of story that now all these middle points, they cancel with each other, and all we're left with is the f of b minus f of a. And all these guys in the middle, they cancel in pairs. And that's our result. So that's not obvious, because how can we relate area with antiderivatives? Well, you say what? Well, that's fundamental theorem of calculus. And that's the last thing I wanted to mention today, so I'm going to stop. I think I overloaded you, I know, because we actually went through probably about 2 weeks of Calc 1 today already. So I know it is getting too much. It is just, I don't want to overload you, but it's all recorded, so it's worth to look at and maybe do one of these antiderivatives and other things. So I'm stopping the recording, and that's the goal.